Kuhn, feel free to guide me. I think we can just have a look at the main components and then look at the neutronics and thermohydraulics behavior of the reactor. Please stop me if anything is not clear or for any question. The main components involved in the core behavior analysis, besides the core, are the pump, the heat exchanger, and the loop and the valves, along with the drain tanks. These are the components involved in what we are looking at today. The can life is limited by the graphite degradation. The damage in the graphite is induced by a combination of um, high energy neutron irradiation and high temperatures. Usually the behavior of graphite is to first shrink in size and then swell or expand. This is related to the relocation of defects and vacancies and interstitial in the lattice of the graphite. This lets the replacing of the graphite and so of the can. We can skip the main values for the reactor and move straight to what happens inside the core from a neutronics and thermohydraulics point of view. As Lars was pointing, this is not the latest version of the logs. These refer to a previous version which is presented as a result in the present presentation. The numbers might be different, but all the phenomena and general behavior applies to the present reactor. So this is a perfect case study to show the behavior of the ThorCon reactor. This hexagonal log is not any more of this shape in the present design, but this hexagonal log is constituted by graphite acting as moderator in green and by fuel passages. Here the fuel passages are small gaps between different slabs. In the present design, there are gaps and holes, but the behavior is the same. The fuel is heated through its path along the 3-4 meter slugs from bottom to top, reaches the maximum temperature, is heated due to mainly fission, and graphite is also heated by gamma and neutron irradiation. So the salt, which is the fuel, acts also as main coolant for the graphite. A variable fraction of the heat, let's say around 5%, is released in the graphite. The temperature of graphite increases the irradiation damage due to neutron at high energy. So we are interested in keeping a low graphite temperatures. The core is constituted by the main logs and refractor logs. This is still the same in the present design. The thermal expansion of the salt and the heating of the salt causes two different feedback. The sum of the two leads to around -2 ppm per Kelvin. The Doppler broadening is, as an usual reactor, related to the broadening of the resonance in fertile materials, namely uranium-238 and thorium-232. The broadening of the resonance in the resonance region increases the probability of capturing and significantly reduces the chance of neutrons to be thermalized and producing fission. The fuel thermal expansion has itself two different effects. By expanding, the salt reduces the effective density of salt inside the core. This increases the probability of leakage by a smaller amount and also increases the effective moderation in the core by reducing the effective fuel to moderator ratio. This might have a positive effect. Nonetheless, the sum of the heating effect on salt is always negative and around -2 ppm per Kelvin. There are some variation depending on the fuel to moderator ratio and depending on the specific heterogeneity, but that's effectively an average value for the core. Also, graphite has a reactivity feedback. The effect of graphite heating is related, it's twofold. The first effect is related to the thermalization of the neutrons, that when the moderator is exposed to neutrons, leads to an effective equilibrium between the thermalized neutron and the temperature of the graphite carbon lattice. Heating the graphite shifts the Maxwellian distribution of the pseudo-equilibrium of thermal neutrons, and this moves effectively the thermal spectrum of the neutrons. Also, the graphite expansion, let me go back to these slides, effectively pushes a little bit of salt out of the core. Both effects are summed up and lead to a negative overall effect in the present design. And again, this is a reasonable number which undergo minor changes depending on the specific core configuration. We're going to have a brief look of the main components of the variable in the analysis of the core. I'm going to use this video. Please let me know if it's clear enough to introduce the main phenomenon in nominal operation. Again, this is published materials. You can find this in the ThorCon website. Does not refer to the latest design. It's the hexagonal log design, but serves very well the purpose of describing what happens. Let it load and let me know if you can see it. Sorry, it's coming up. So this is the distribution of the fission power. Let me pause for a while. In common reactor of pseudo-cylindrical shape, we expect the distribution to follow a cosine towards the z-axis and a Bexel function toward the radius. And this is what we have. At the center, we have the peak of the power, and we have lower power density in the bottom, in the top, and the radial periphery. In this specific design, the control rod were inserted in the center, and there it is where you have a reduction of the power distribution. In the present design, the control rod have moved, but the similar behavior is still seen. So we have a standard distribution of power. The fission power heats the salt, and this is the fission power in the salt in the gap. And this is used to calculate the temperature distribution of the salt. And so the temperature distribution of the salt is different from the power distribution itself, because we have the power to precisely choose the flow rate in each of the hexagonal logs, or the flow rate in each of the present-day design log. This is done as much as we can to flatten the temperature distribution and to have an outlet temperature which is as much as possible uniform radially, to have a uniform outlet temperature of each log equal to the maximum fuel loop temperature. And this is what is shown here. For the outermost periphery, the maximum temperature is not reached even with the minimum allowable flow rate. So we have a smaller amount of salt exiting the core at a slightly below temperature compared to the maximum. The graphite temperature, as we were saying, is determined by the temperature of the salt, which is cooling it, and the amount of photon and neutrons hitting it and eating it up. So basically, the graphite temperature is obtained starting from the local salt temperature plus the amount of energy released divided by the effective heat transfer coefficient between the graphite and the salt. The design of the specific log is a trade between optimal moderation and optimal heterogeneity, and being able to cool enough the graphite. Once again, too much of high graphite temperature results in a faster than acceptable neutron damage, which consists in shrinking and then expanding again due to the defects and relocation movement. But we can analyze the graphite temperature in a similar way. The analysis presented here, even though they refer to a older design, reflects exactly what is the analysis that ThorCon is conducting on the present day core based on the Monte Carlo code Serpent and the multiphysics tool OpenFOAM to keep track of the salt and graphite temperature along with the neutron flux. I don't know if this video helped a little bit understanding what is the main part of the flow, the main temperature distribution, and the power distribution. Please let me know if anything is not clear, so that we can assume this is the understood behavior and move on. I don't see anything in the chat, so I go ahead.
Manu,
Please.
usually people ask after it's over.
Oh,
So,
sorry
yeah,
about that.
yeah.
Copy that. Thank you very much. Sure. Um, so this is the core, of course, the main component of the primary loop. Let's have a look of the other component as well. The pump and the header tank are located above the core. So this is the pump, and it serves the purpose of moving the salt around the core. The circulation time, again, is changed in recent design due to more accurate estimation of the salt capacity, but let's say is in the order of 10 seconds to 15 seconds recirculation time. That means that we have to move around more or less 1 cubic meter of salt per second. So that dictates the requirement of the pump. And the header tank is placed again on the top part of the primary loop and provides surface area to facilitate the removal of gas from the salt. So basically, it provides a space for salt to gas interface. There is a continuous purging of helium, currently set at 2 liters per minute. We will see in a few slides the path of the off-gas system and the behavior of the decay in the different components. The main one of the main reasons for this is the continuous removal of xenon-135. As you know, xenon-135 is a huge neutron absorber and has a large impact on a uranium-5 fueled thermal reactor. In solid fuel reactor, your xenon-135 is bound to stay within the fuel, and the reactor operation, especially in changing power, is dominated by the behavior of these nuclei. We'll see in a while that this effect is much reduced in the ThorCon reactor due to the fact that the header tank is capable of effectively removing it from the fuel. Part of it is absorbed in the graphite. The exact amount that will be absorbed in the graphite depends on the specificity and porosity of the graphite is not known perfectly right now. So different hypotheses on the xenon-135 intake into the graphite are being made and included in the reactor analysis. Besides effectiveness on the reactor operation, removing gaseous fission product has a huge effect on the reduction of the source term in case of accident. The primary heat exchanger, as mentioned before by Lars, has moved from the side of the core to the top. The primary heat exchanger is made by a U-shaped shell and tube heat exchanger. The adoption of twisted tube is due to the enhancement of the heat transfer coefficient on the shell side. The fuel salt stayed in the shell side and the secondary salt stays in the tube side. In case a leak will send the secondary salt in the primary loop rather than the opposite. Also, the management of the decay is facilitated by having the fuel in the shell side. The freeze valve is a feature that has been adopted since the beginning of the era of molten salt reactor. In a simple word, the freeze valve is just a pipe that is occupied by solid fuel that has been frozen and constitute a barrier for the flowing on the molten salt above it. The freeze valve acts passively as it is continuously refrigerated and cooled by a flow of helium that keep the plug of salt cooled. As soon as this active flowing of helium is interrupted, either voluntarily or due to the stopping of available power, the heat in the heat capacity surrounding the valve starts to flow through the valve to the plug of solidified salt until the salt melts and the valve is open. The design of the valves is taken directly from the Oak Ridge era, so the operation of this valve has been already tested in real application and determined to be reliable and replicable in the sense that the time for the opening of the valves might not be known at the accuracy of the second, but is can be estimated and is reliable in a reliable way. The number of valves are selected in order to have a draining time acceptable for the transient that are being studied. In the present design, there are 4 valves that copy the Oak Ridge design here. This picture, again, all this is public material, shows in the detail the design of the valves. This is the specific section where the solid plug is present. Once the valve opens, due to the absence of active helium cooling, just by gravity, the salt drains in the drain tank. The drain tanks are the tanks below here. We are not showing presently in this picture the the lines that delivers the flowing salt from the valve outlet to the group of drain tanks. But the drain tanks are those cylinder. The drain tanks are the green vertical cylinder partially shown here. Once the valves are open, the drain completes in approximately 10 minutes. The draining time depends mainly on the amount of salt, the viscosity of the salt, and the density of the salt. These physical parameters have little impact, though, on the time of the draining, which requires around 10 minutes to complete. This provides a strong safety feature for the drain. I can show you a volume equivalent picture showing what happens. First, the drain, the header tank. Let me go back a second. This is a volume equivalent. This is not the core. This is a cylinder who has the same volume of the salt contained on the core. And this is for the heat exchanger in a similar way. At the present design, the heat exchanger was still, at the design showing this picture, the heat exchanger was still vertical. First, the header tank is emptied. Then the pipe completing the primary loop below the valve. Then the primary heat exchanger is emptied. And finally, the core empties. These all happen in approximately 600 to 700 seconds. And the flow of salt is stopped after 700 seconds, and all the salt is in the drain tank. The salt in the drain tanks evacuates heat mainly due to radiative heat transfer. The drain tanks are surrounded by steel walls that are effectively cooled and submerged in water. There are walls outside and inside of the drain tank screw. So effectively, the drain tanks can see cooled wall on both sides. The view factor from the drain tanks to the cool steel walls is rather high, higher than 50%. So the drain tanks release heat mainly due to radiative heat transfer and can grow rapidly. The heat's delivered based on the maximum temperature of the salt. This refers to a previous design, but with the current design, the difference are minor and related only to geometry, not to the behavior. As you can see here, the peak temperature is reached in the salt in the drain tank just below the top free surface of the salt due to the convective movement of the salt within the drain tank. The hot walls radiate heat towards the surfaces of the steel walls cooled by circulating water. It is expected that water reach a boiling temperature and nucleate boiling increases the rate of heat removal. Not depicted here is the circuit of the water going and steam going towards the pond and releasing heat in the pond that provide a long time heat capacity, and finally to the air in the following time. Going back to what happens during the draining, we can see that another effect of the draining is, of course, the reduction of the reactivity of the core. Let me zoom a little bit this picture. You can see here the reactivity of the core during the draining. At this time, the draining line reaches the elevation of the core, and we can see that the core starts emptying. This slowly but steadily introduce negative reactivity that definitely stop the power in the core. Of course, in most accidental scenario, the reactivity of the system during a draining, it's already severely negative and the power has stopped due to the introduction of negative reactivity due to control rod and to the negative reactivity feedback due to the heating up of the salt. So in most scenarios considered, the negative reactivity introduced by the draining of the salt is not required to shut down the reactor. Once the salt is drained in the drain tanks and they are effectively exchanging heat with the cold walls, we see that at the beginning there is a rise of the temperature due to the decay heat. You can see the decay heat in this line reading from the right. This is the decay heat in megawatt, and this is the time in minutes after the shutdown of the core. So up to several minutes after the shutdown, the power is in the megawatt order of magnitude, and the heat has to be released to the cold wall. This requires a rising of the temperature of the salt and so the temperature of the drain tanks. The main sizing criteria is now the creep damage of the drain tanks. The stress level is relatively mild, but the temperature follows this behavior, rising at the beginning due to the higher decay heat and then slowly going down as the decay heat decreases. The calculation of the creep lifetime is done based on an available correlation for the creep that relates the maximum stress or the von Mises stress and the temperature. The creep is calculated both in the position where the stress are maximum and the position where the temperature are maximum. and we see that in any relevant scenario, the creep damage in the drain tanks is relatively mild, well below 1% of life. This is a sketch view of the drain tanks, and one of the questions that has to be answered is the possibility of criticality of the drain tanks in case of a leakage that introduces accidentally water in the system. This is an unlikely scenario, but nonetheless, the reactivity of the drain tanks full of salt, also considering the mixing with the makeup fuel, is way below 1. So there is no possibility of criticality, even in case of flooding of the entire space surrounding the drain tanks. So this is the power distribution. The profile shows a much higher values in the upper part of the core, which may not be beneficial for common reactor design. No, there is no shift towards the top of the reactor. From what we can see in the picture, is fairly symmetrical between the bottom and the top. Indeed, there is a slight shift toward the bottom because the cold salt in the bottom side has, let's say, a local higher reactivity, in the sense that the higher density there and the lower temperature result in total in higher local reactivity, whereas the slightly higher temperature on average on the top of the salt result in slightly higher Doppler effect and negative reactivity. Since the neutronical dimension of the size are not too large, the imbalance between the top and bottom is relatively mild. No, yes, that's the temperature distribution. I believe you were referring to this one, which is the temperature distribution. I'm sorry, I'm not able to put full screen due to the problem in my Linux system, but yes, this is the temperature distribution, which of course is unbalanced towards the top, but not the power. The power is fairly symmetrical, and if any imbalance, the imbalance is toward the bottom. If this answers the question, I go back to the presentation. Sure. And so the effect on the neutron economy of the delayed neutrons leaving the core is rather mild. Say we are losing 0.03% of the neutrons due to this move. On the other hand, it has some effect on the control of the reactor. This is related to the fact that we are finally adding an effective delayed neutron fraction, which is slightly lower. In particular, at nominal flow rate, the effective delayed neutron fraction reaches value of around or below 300 ppm. This number should not pose any problem. They are actually not much lower than what we see in solid fuel fast reactor, in which the contribution of plutonium isotopes and minor actinides severely decreases the delayed neutron fraction. Nonetheless, what is peculiar is not the small value of the effective delayed neutron fraction, but it is the fact that the delayed neutron fraction effectively depends on the flow rate. So since it is possible, in principle, to operate the reactor with a variable speed pump and a variable circulation flow rate, even if this is not in the present control design of the ThorCon system, in that case, we will have to take into account that reactivity beyond the reactivity feedbacks due to temperature is changed and introduced due to the different flow rates. And effectively, if we stop the circulation, either voluntarily or by accident, around 300 ppm of reactivity, or slightly above that number, are introduced due to the fact that the delayed neutron precursor that used to decay in the primary, it exchanger or in the piping, or even in the periphery of the core, are now decaying inside of the core. So effectively, once we stop the pump, keeping in mind that there is inertia that keeps the flow circulating for some time, the reactivity is inserted corresponding to the difference of the reactivity of the difference in the beta effective between the static condition and circulating condition. This is a well-known feature of molten salt reactors studied since the Oak Ridge area. So we just have to take this into account during the analysis and the design of the control system. Uh, it might be a little tricky for all of us coming from solid fuel reactor experience. So if you have any question on this specific issue, I will be happy to discuss more in detail. Otherwise, I move on. Let's analyze, see if anyone has a question. Otherwise, I believe we do that at the end. Let's analyze what happens with xenon during transit. The fact of xenon as a strong absorber, I apologize for not being able to put full screen, so I'll try at least to put the picture at the maximum size I can. Of course, the ThorCon will distribute the presentation at high quality and resolution, so you will be able to look at this. Let's imagine a change in reactor operation with the reactor, ThorCon reactor that has been operated for in steady state for a long time, let's say for 15 days at full power or 100% nominal power. In this case, the xenon in a solid fuel reactor would reach a well-known level that just depends on the amount of iodine-135 that is produced from as fission fragment and fission product decay chain, the amount of xenon-135 that is captured by that is destroyed by neutron capture, and the amount of xenon-135 that naturally decays. In circulating fuel reactor, and specifically in the ThorCon reactor, where the ether tank plays the role of removing gaseous fission product, the calculation of the effective content of xenon-135 is more difficult. In particular, it has to be defined and confirm the effectiveness of xenon-135 removal through the surface gas to salt surface interface and the amount of xenon that reaches the graphite pores. This is not perfectly known at the present moment. And nonetheless, we can make hypotheses and assume two different scenarios. One in which we have a very fast effective removal rate, and one in which we have a lower effective removal rate. In both cases, after 15 days of operation, xenon-135 reaches an equilibrium value. We are calling the xenon-135 mass as the effective mass of xenon that will be present in the salt, giving the same reactivity effect. If part of the xenon is not present in the salt but into the graphite, its effectiveness is slightly higher due to the slightly higher thermal flux there. So let's call this the effective xenon-135 mass. Let's see what happens when we drop the power virtually instantaneously at day 15 from 100% to 50%. So what happens in this case, as you can imagine, is that the production of iodine is dropped from the equivalent equilibrium values at 100% to the 50% value. And so slowly, the fraction of iodine reduces. And let's assume for both cases two scenarios. One in which we keep the removal rate constant. Let's start from the orange line here. So if we drop the power instantaneously from 100% to 50%, and we keep removing xenon with the same effective rate we were assuming for the steady state operation in 15 days, slowly the system adapts to the new level of xenon decay rate coming from a reduced level of um, iodine production. You can barely see a slight increase here at the beginning. This is due to the minor fraction of xenon atoms that are removed by neutron capture. At the beginning of the change in power, the xenon 135 level is almost constant because it has not changed its equilibrium value at all, and the fraction of xenon removed due to um, neutron drops by 50%. So you can barely see this increase because in the ThorCon reactor, the amount of xenon removed by neutron capture is very small, almost negligible. So in the case where we have a medium effective removal rate, for example, meaning that a significant fraction of xenon is indeed absorbed in the graphite, if we keep removing at the same rate, well, slowly, with the time constant related to the decay of iodine into xenon, we will adapt to the new value that is roughly more or less half of the equilibrium value of the xenon concentration at nominal 100% operation. On the other hand, if we adapt our removal rate, so in a simplifying term, the amount of salt flow that is flown in the ether tank or exposed to the salt to gas interface. If we halve it effectively, after we reach equilibrium, we will go back to the same xenon equilibrium concentration that we had before the change in power. So in a simplified way, regardless of the possibility of removing fast or slow the xenon, so regardless of the effectiveness in removing the xenon, we can assume that the ThorCon reactor, if it's possible to tune and change the effectiveness in removal in response to a transient, we will always be able to maintain a net zero reactivity effect. Let's analyze this case. This is the reactivity change due to the change in xenon effectiveness. And this is the net reactivity effect due to xenon absorption. This is the fast effective removal rate, so the xenon effect is very small, below 100 ppm, compared to the 1000 ppm of, for example, a PWR or an HTGR, for example. Well, in those cases, if I stop, if I keep on removing xenon at the same rate at day 15, the concentration of xenon, as we were seeing in this picture, drops. Sorry, the mass of xenon increase if I move to 50%, whereas if I keep removing with the same rate, the concentration drops. And in the two cases, I will either slightly move to half of the effective reactivity loss, or have a peak at the beginning and then go back in a few days to the same equilibrium value. What we are implying with this description is that if the ThorCon system is capable of tuning constantly the removal of xenon, depending on the time constant for in the graphite to migrate back to the salt, we are capable of ensuring an almost zero reactivity transient. So the effect of xenon can be managed. It is very small to begin with, and then it can most probably be handled regardless of what will be the effective fraction of xenon that goes into the graphite. This is one unknown right now. It is not exactly known the fraction of xenon that will permeate in the graphite. The graphite is treated in a way to close as much as possible the pores, but even in case part of the xenon goes into the graphite, we know for sure that its effect will be much, much milder than solid fuel reactor. And we expect no forced shutdown period after an accidental change in power due to the xenon peak like we have in other reactors. Again, if you have any question on this,